ICCF-7. My name is Fred Yeager, and I'd like to go over a few administrative details before I turn the podium over to Professor Mallove. In case you haven't already located meeting room 1 through 3, it's upstairs one floor on the south end of the building. Breakfast and lunch will be served there, and you can get there by taking the escalator to the right as you exit this room or to the left through the lobby. Morning and afternoon refreshments will be served next door in ballroom B, along with the poster display boards. And during the week, there'll be various organizations videotaping the proceedings. And if for any reason you do not wish your presentation to be recorded, just simply tell the people in the back of the room ahead of time. Our registration records show there are over 55 new persons, or about a third of the total audience, who have never attended an ICCF conference. I urge you to make a special effort to get to know these newcomers and make them feel welcome here. And it is especially heartening to have 9 students present, many of whom will be giving their very first presentation at one of these conferences. All newcomers provide vital, fresh perspectives that are necessary to ensure continuation and growth of this challenging field. There are also some of our colleagues who are conducting research and who have submitted abstracts, but were unable to be here this morning for financial reasons. And along those lines, I'd like to share a personal thought with you. Participation in the organization of ICCF-7 was a tremendously rewarding experience for me. It allowed me to get to know many of you on a much closer and personal basis. And what constantly impressed me throughout the process was your universal and intense interest to investigate this field, with efforts driven by curiosity and a strong desire to learn. Many of you have suffered professionally, financially, and I suspect in your personal and family lives in order to pursue this field. And why did you endure all the pain and suffering? I believe it is basically your unshakable quest for knowledge and understanding, and to find a better energy source to support mankind's needs for the next century. I admire your perseverance, dedication, and personal sacrifice for this worthy cause, and I consider it a profound privilege to know and to work with you. And 9 years after the initial announcement, we are still seeking a fuller understanding of the first-hand results many of us have observed in the laboratory. I hope our program this week will help guide your research, sharpen the focus of your thinking, and make your continued efforts more productive. So enjoy your week here in Vancouver in a spirit of open-minded learning. Renew old acquaintanceships and make a few new ones. I'd now like to present Professor George Mallove, Director of Fusion Studies at the University of Illinois and editor of the American Nuclear Society's publication, Fusion Technology. Thank you.
Thank you, Fred. I want to add the welcome from the program committee to you for attendance here at the meeting. I just have a few bookkeeping announcements. First of all, we have a full program, as you can see, and so it's important we keep the time schedule. So the session chairs have all been instructed to do something drastic if the speaker runs over. Please don't. The second thing is, as you see Dr. Kane sitting over here as the next speaker, we have arranged so that the speakers will come to this preparation area so it will be easier and save time getting up onto the stage. So the next speaker after Bruce should go over there as he comes up here. We would like for people presenting the poster sessions to have those posted in the morning as early as possible before the morning break. And they should be taken down by 6 p.m. in the evening. In addition, those oral presentators should remember to put up some materials as their post PM follow-on poster session. final thing has to do with the proceedings. As you know, we are trying to keep a very tight schedule for the proceedings. So we hope that you have your papers here. If you don't, there's a strict drop-dead deadline of the end of the month to get it to us. Now, Hallie Coppage, who's in the back, Hallie, could you stand up? It is handling proceedings, and she will receive them here at the meeting, and she'll have be at a table in the mornings outside of Ballroom B to receive manuscripts. Please give them to her. If you're going to mail them in, please discuss where to mail them, how to handle that, and when you're sitting with her. Well, with that, we're ready to begin, and the session chair with myself for first session needs no introduction. Dr. Martin Flashman will help handle this. So I have the pleasure of introducing Dr. Bruce Kane from Mississippi State University, and he's going to be talking about thermal power produced using thin film palladium cathodes in a concentrated lithium salt electrolyte.
Right up to see for everyone? Okay, I'll go ahead and get started. Again, I'm Bruce Kane from Mississippi State University, and I want to thank everyone for inviting me here. I've never been to an ICCF conference before, so I'm one of the newcomers that Fred mentioned, and I'm real pleased to be here. I thought I'd show you today some experimental results. I'm not a theorist, and again, I don't try to act real knowledgeable on exactly what's going on to produce thermal heat, but I'll show you some experimental results where I set up essentially to sort of mimic the Ponsman-Fleischmann type of cell, and some of the changes I've done to actually get some of the heat. And then before I finish up with a lot of questions that have shown up recently in terms of repeatability. But I thought I'd mention some of the co-authors of this paper. Mike Grigsby at the University of Alabama at Birmingham has been involved in putting down these thin films. And then, of course, Roger Kane and Monica Millen are engineers out of Huntsville, Alabama, have been quite involved with some of the engineering discussions with this. First thing I thought I'd do is recognize some of the experimental pioneers. Martin Fleischmann and Stanley Pons. Obviously, that's one of the starting board for just about all this experimental work. And certainly the ideas that I have, you'll see, is basically a cell with an anode and cathode, run current through it and see what happens. I thought I'd just mention the pioneers that are central to this work. My outline today is going to look like this. I just talked about, primarily cell design and hardware. See how the system is set up, so some photographs give you an idea of how large the system is and how it's put together. The palladium film details, see exactly what some of the grains and crystals look like, and then primarily focus on the cell operating conditions and the thermal power evidence. And then after that, talk somewhat about heat versus no heat run, because I've been, like many of us, quite frustrated with runs that should be identical to the ones that work that don't produce heat. So I've had both positive and no results. And then focus a little bit on why I think no heat is coming from my particular setup. Some differences, critical differences between the ones that did produce heat and those that didn't. And then I'll follow up with some conclusions. Okay. The basic cell design and hardware, it's basically an electrolysis cell, simple cathode and anode. I have an anode that's grounded and then push my cathode negative and run current through that. And it's typically done on a duty cycle type of system where during the duty off cycle, I measure the cell resistance using a 4-wire resistance measurement. The instrumentation that's in the cell itself is a cathode film resistance measurement, the electrolysis scheme itself, and then I have a reference electrode, a pH electrode, cell temperature probes, both high and low in the cell, and a flow calorimeter is used to actually heat the system up and cool it down. And of course, it's all computer controlled data acquisition. And then I have some cell photographs to actually see what this thing looks like. But this is probably the biggest overview type of figure of the system. And what you can see, I guess the two main things, of course, is the cathode, which is basically located centrally near the bottom of the cell, and there's the anode. And I typically bias these with a DC power supply, and the anode is tied to ground at one point there. This whole system is set up with a 2-liter tempering beaker. It's quite large, so that when I actually fill it up with solution to cover the electrodes, it's about 1,200 milliliters of electrolyte to cover those. And what I've shown schematically is the 4-wire resistance readings. Essentially, I take, if you take a piece of sample, which is roughly 1 inch by 2 inch, I take current and voltage readings here. Let the current come in, current come out, and then I read the voltage drop across the corner. So it gives me some idea of a 4-wire resistance of the film. That's sort of the way things set up. The other things you can see in here, I have a purge gas manifold. We can put a blanket over the top of the cell, or a Teflon cap. And notice that it's vented. So this is an open to air type of system. It's not a closed cell. And schematically, I've just shown the pH electrode and reference electrode. Those typically are immersed about 1/2 inch down into the solution. So they're really sampling the pH and reference at the very top of the cell. And let's see what else. I've got 2 RTDs that are put down into the solution. Again, one of them high and one of them low in the cell. And then the last thing I thought I'd talk about is the calorimetry itself. Essentially, it's just a big flow loop. It's got a pumping system with a heater, to which I've also added a tank with a reservoir and a chilling coil. So I can run this thing basically from about 10 degrees centigrade to 70 degrees, something like that. And it runs through, and on the input, there's several RTDs that are averaged together to get the readings on the input, and similarly on the output, and then a flow meter that monitors the flow rate continuously during the experiment. And the results I'm going to show today have some differences, and I thought I'd point them out. Some of the early runs had 2 thermocouples on this input instead of the 5 RTDs, and 2 thermocouples here. So the results have a little bit more scatter than the more recent results I'm getting. But you'll see that, I'll talk about that when we get to it. You'll see some of the results of how the temperature varies even with not producing heat. Okay. This is a photograph of the palladium itself. These are 2 typical ones. I thought I'd just show them so you can see what they're like. Again, I put a ruler up here for a scale idea. But the basic sample before it's coated is 1 inch by 2 inches long. And this is a sample with a thin film palladium on top. And just an example of what it looks like after it's reduced heat. And what you see is this real darkened area in the middle. And just for comparison, I've also done a few runs using regular palladium foil, which did not produce heat, but they also turn very dark, like you see here. Okay? And how those samples are mounted is shown here. It's basically a big Teflon arrangement. You see here in the front, this is the anode. Here's the reference electrode in blue. And this piece right back in here is where the sample is mounted, and it's just clasped together with bolts to hold it into place. And along the side, you can see several of the wires coming down that actually do the resistance reading and also provide the current readings. And then this down here is just a side view of the same thing. Again, this is a low temperature reading, and this one up here reads temperature higher in the cell. And then back here is the pH electrode. This is taken without it actually in the cell itself. Okay. Now when you mount the cell into the calorimeter, I just took a couple photographs of what it looks like. And what you see is an insulating box and the basic 2-liter tempering beaker here, and mounted in there, this is with no solution in it. You can see the basic Teflon arrangement in various parts. And I have a mirror at the back so I can see a little bit from the back side while this thing runs. And of course, to complete the calorimetry, I close this thing off of a cover when I need to close it up a little bit. And then up here is just electrical hardware to get the readings. Now, typically what this looks like when it runs, this is one with no heat being produced. This is just a typical electrolysis with probably like 2 or 3 amps running through it. I didn't get my camera set up until after I actually got the good runs that took off, and then the last set that didn't work. But I thought just to see what it looks like, where you see these micro bubbles all in the top. It's typical oxygen and hydrogen, we call it. Now, the palladium itself, I'm not going to focus too much on that today. There's quite a bit of detail, but essentially it's a palladium. It's 5 microns thick on aluminum oxide. It was sputter coated by Mike Ridgely at the University of Alabama, basically on 70 degrees centigrade deposition temperatures, which means these films, once the crystals start to grow, they freeze real fast. So we end up with very small grain sizes. Have a good low base pressure in the system, and they're pre-cleaned in an argon discharge. We'll end up with polycrystalline grains. I'll show you some photographs of those. Average grain size is shown here. And we did do some runs where we're essentially changing the anneal character. Some of these acid positive and some anneal. And after they're anneal, they are fully anneals. Some analysis before they're used, basically we found there's mostly palladium, some carbon, and some oxygen. And then after electrolysis, this is some interesting results that are shown up. And use some water. Basically what's finding is we get a lot of oxygen and carbon, some silicon and palladium, and some interesting traces of lead and calcium are showing up. I thought I'd use the photos. Thank you. Much better. This is a typical photograph of an acid-positive film. We made several of these. One at the top, you can see the basic scale on this. This is a 10 micron scale running from here to here. So the basic grains, you can see the largest ones are no more than 2 microns in size. And they're just basically uniformly polycrystalline with what's called a log normal distribution throughout. What I did was just took this, 10 microns, and blew it up, took another one at 20,000 by magnification. And this one has a pretty good detail of what the grains look like. You can imagine the amount of surface area that's embedded in this. So what you see are some of these larger grains that have started to grow, and then a whole bunch of these down in here that are very, very small, incredibly microcrystalline. So it's somewhere between an amorphous and microcrystalline type of structure. And again, this is a 2 micron scale here. So this sample, this particular large grain is maybe 1 to 1.5 microns across. Because that's the typical as deposited right out of the deposition chamber, is what they look like. Now, to give you an idea of several of these after electrolysis and after producing heat, this is one. Again, this is just a photograph of the surface. Now, again, just to give you a scale comparison, this top one, this is on a 5,000 by scale. Again, you see the 10 microns is roughly from here to here. And if you take a look, compare it with this, 10 microns is roughly on the same scale, 1 inch or so across there. So what we're seeing is those grains completely covered up with a whole lot of stuff. And the question is, of course, what is that? It turns out most of this that we see on here, let me show you a little bit of a blow up at this same region. You can see there's sort of a crystal structure. And this basically is mostly lithium carbonate. And again, that's a central feature I'm going to focus on today and talk about is the carbonate that formed. I was a little surprised when I saw this amount of it showing up, but it definitely forms all over the surface here. It could also be a lithium oxide, which is also a white crystal. The black material, again, remember the photo I showed you where it looks black. In fact, when it first comes out, it looks like it's sort of like been a barbecue pit of the sort. The black is apparently carbon and palladium oxide. Those are the 2 things that make this thing look dark. Then up close under a microscope, you see a lot of this more white crystalline structure that's on top of it. And it gives you an idea, again, the magnification on this one, there's a 10 microns right there. So this is backed up. These are very large pieces that we're looking at. A lot of lithium carbonate that's stuck to the surface. Okay. That one was for an as-deposited film, which means there was no annealing. I also did a few runs with annealed palladium. This is a typical one that was annealed for an hour at 1,000 degrees centigrade. And again, the scale, this is a much larger scale, 20 microns here. So these are the grains basically are starting to relax and grow. You're seeing the equax grain structure. This is again just one showing a little bit more magnification. We see several large grains growing and again smaller ones, but this is just real typical of annealed polycrystalline materials. So I tried both of those in the system to see if there was any difference. And here's one with the as deposited, or the annealed coating after electrolysis. And what you see are some of the same types of things we saw on those that were as deposited. Is you see the large grains, but there's also evidence of some black and white lithium carbonate stuck to the surface. Now this particular sample was actually a lot darker before I pulled it out of solution. What I did, this one produced about 100 watts over an 8-hour period, and then near the end I briefly did a reverse bias. And when I reversed it, this thing cleaned up in solution quite a bit. So we don't have the full spectrum of all the debris on the surface. I think it cleaned up quite a bit at the end. As you can see, again, that same evidence of some of this white stuff that's stuck to it. Now, cell operating conditions, I just thought I'd make a list of how things run. Temperature, basically from 10 to 60 degrees centigrade. What I've found is that typically if you force this stuff up in temperature and down in temperature is when I see the heat start to form. Typically at steady state, it doesn't want to do that. The electrolyte is also a little different than several I've seen before. It's a lithium hydroxide monohydrate in D2O. So at the very beginning, I have H2O in the system. In fact, it's about a 5% mole fraction. It comes out to a 2.5 mole solution in terms of concentration. So I think that's a key feature that may be different from several others that have been done. Highly concentrated lithium hydroxide. The pH runs 12.5 to 13 at room temperature. Now the calorimeter itself, it actually can run anywhere from about 0.2 liters per minute up to about 3 liters per minute. But the data I'm going to show today is in this range. It's basically 0.4 and 0.8 liters per minute. And it gives me a calibration sensitivity. Well, the calibration is done with a Teflon immersion heater. Just put an immersion heater in there and keep track of the power in, power out, and calibrate the thing. I found this calorimetry is about 90% efficient. If I put in, say, 500 watts, I can actually detect the 450 of that. The sensitivity for the data today is about 75 to 40 degrees centigrade per kilowatt. And these are large numbers in terms of the power. My motivation for making the calorimeter this heavy duty was to make sure I didn't get in any runaway type of situation where this thing just boils away and you lose all your data. So I kind of opted to make it's not a very sensitive calorimeter. It's designed to remove a lot of heat. And so it makes it where it's not real good for picking out, in fact, less than about 20 watts. If you get more than 20 watts, you'll definitely see it. 5 watts is something buried in the noise with this thing. And the way it's operated, the duty cycle, typically 60%, every 30 seconds, 60% of that time, I have the current going when I'm electrolyzing. And then it's turned off for 40% of the time where I go through and resample all the voltages between the reference and the cathode, and also between the anode and the reference electrodes, and then do the 4-wire resistance measurements. So I kind of have an off-time measurements and an on-time measurements. And that happens both with or without the electrolysis current turned on. And two of the things I'm going to focus on a little bit later is what I call the VCA. This is the cathode to anode potential and the reference to anode potentials. Those are two things that turned out, I found out much later digging into those that did not run, that there are some central voltages that tend to show up when this thing is going to fire and when it's actually producing heat. And there's certain voltage ranges that don't work for this particular system. Okay? And again, just to remind you what that is, let me pull out that one figure. We can kind of go back to VCA and VRA. I'm going to get into that in some detail in just a minute. The cathode, the CA, is just essentially the cathode to anode potential, and it's measured at these electrodes. There's actually separate wires that run down, so we don't have any IR drops down the sleeves. It's measured at these electrodes, and then the reference to anode is just the reference potential to the anode potential. The reason I picked the anode is just because I happen to have grounded it electrically. So everything else floats wherever they want to float at, or their power to. So I'll keep that slide out. I think that's a good one to keep track of this thing. One last thing I thought I'd mention is the current density. Typically, the current density depends on what you want to do with it. What I want to show you in just a little bit is that some of the heat runs I've got produced heat without putting electrolysis current into the system. An incredibly surprising result to me. There's other runs where you have to electrolyze it quite a bit, and then during some of the non-electrolyzing time is when the power showed up. That's just external results I've found. But typically I can run anywhere from about a milliamp per square per centimeter squared up to maybe half an amp. That's the most I've ever done. Because a lot of times when it doesn't produce heat, you start trying all kinds of things, just see what you can do to it. And at most, that the 0.5 is a very large number, and that's probably on the order of 4 amps DC running through the system. And most of the data today is more in the 100 milliamps per square centimeter, and maybe even 50 milliamps. You'll see a various ranges. But typically, if you get up to this level, you're just blowing away a lot of hydrogen and oxygen. So I try to stay a lot lower. Okay, so those are some operating conditions that I think are quite useful. Now, one of the biggest sources of information, sort of in retrospect, after I had several runs that did not produce heat, was to go back and find what's the difference between those that do and don't. And one of the key indications was visual information. So I made a couple of things to compare this cell, the way it appears during heat generation compared to when there's just electrolysis going. And I thought I'd just kind of go through this because I think this is a central part of how we're getting heat in this system. First off, I have the tempering beaker and noting that it's open to cell, so we have the exchange with the atmosphere. What we see at the beginning, and this is one during heat generation, and this actually occurs without any current running. Quite surprising. You'll see this micro bubbles. In fact, I mentioned this region in here from the top of the solution to maybe 2/3 of the way down. It's a region of very fine micro bubbles, typical of what you'll see when you run an electrolysis cell. These bubbles that just form, and basically they're hydrogen and oxygen that are entrained in the system, and they're swirling with convective motion. At the very top is what I call a precipitate formation layer. You can actually see these large and small flakes of precipitate forming, and they begin to diffuse and fall down. And they are opaque. It makes it where you can barely see through the solution, and these do form and tend to swirl, and gravity tends to make them come on down to the bottom. And what is there? There's a region right in here. There's what I call the clarified solution, and it has very small precipitate flakes drifting down through that, and that's different from the electrolysis one I'll show you in just a minute. Again, this is one with no electrolysis current. There are hours and hours of this thing producing heat, looking just like this. It looks like it does when you're running electrolysis, with the exceptions of this area down here at the very bottom. I call it the very fine precipitate powder form, right here at the very bottom. And essentially it's opaque at the bottom, it's basically pure white, but above it is a very thin diffusion layer, where you can see this stuff, it appears to be dissolving and going back in solution. In fact, one of the characteristic things is staring at this hours on end is that it appears there is some type of exchange between the carbonate being formed up here, the lithium carbonate, coming down, forming, and then somehow re-dissolving back into solution. There's a dynamic exchange going on. In fact, over hours of the run, you'll notice that this layer right in here, the thickness actually grows and then shrinks. Grows and shrinks. Has type of oscillation to it. Just stuff that just surprised me incredibly when I saw that. Again, I'll show this and compare it now with one during electrolysis of how it appears. So this is the key feature. The very fine with the diffusion layer extending upward is the major difference. Now to compare that with the no heat generation with just electrolysis, I can take this same cell and run a lot of current through it, and in fact percolate some CO2 gas on top or whatever, and get a lot of this carbonate to form as well. There are ways to force the carbonate formation, but in this case, these flakes form all very near the surface, and they tend to be very large. None of them are small, they're all quite large, and they just fall. They just fall down through the clarified solution and form at the bottom. Again, during electrolysis, this is with electrolysis on, you still have the region of the fine microbubbles generated by the electrodes. But you also get what I call a granular crystalline form. I've taken both the silty powder form and this crystalline form to the chemical lab. They've analyzed it. It's always lithium carbonate, but they look drastically different in terms of their crystal structure. Well, again, this could be a major difference. This particular material, it forms, and the depth of it in the bottom of the cell just grows depending on how long you run the current. But you can force the carbonate to form just by running current. And again, I think this is something probably many of you haven't seen. I think it depends primarily on the highly concentrated solution I started with. There's a lot of lithium in there, and it can interact with the carbon dioxide in the air and form this precipitate. Now, there was one other thing I haven't mentioned here, that there's no crust formation above the cell solution. On these cells that where you just run electrolysis and there's no heat, the top of this beaker stays as clean as it can be. It's just clean and clear. Whereas those that produce heat, the top of this cell becomes very crusted. In fact, I mentioned it here, the lithium carbonate crust formation on the inside walls. That crust forms and creeps all the way up to near the top and also coats all the wires and cables that are running up there. Completely different than those that it's not producing heat. Again, I can't explain it, I'm not a chemist, but I'm just showing what I observed on this. Quite interesting and quite surprising to me when I first saw a lot of this. Okay. But anyway, there is drastic differences between running it with current and without. The next thing I thought I'd talk about is the thermal power evidence. I have some relatively detailed plots, but basically I'm going to take you through just two different runs. One was using a palladium material that had been in the old at 1,000 degrees, and then an even more surprising one, as a positive run, that actually produced heat with no electrolysis. As soon as the solution was added to this beaker, the power just jumped and took off and ran for about 20 hours. Real surprising. I thought I'd show you this one first. This is more typical of the successful ones I've had, where you did have to go through a lot of up and downs with temperature cycling and current, and finally the heat came out. So I'll show you those two thermal power evidence. One disadvantage of having a computer take all the data is you have a lot of data to plot. And so it's a little bit tough on how to present this in the best way. But I thought I'd walk you through it. I tried to be consistent with the color nomenclature and what have you. But this is a run, I guess, of some things I want to show. What I'm basically plotting, this R4C is the root 4 wire resistance across the palladium. And so if you're interested in loading curves, this dark blue is essentially the resistance of the film. And these arrows then point to which scale we're looking at. All the temperatures are plotted over here on this right scale. So for this particular run, for example, if we just look at the temperatures, this thing over a 35-hour period started down here, the temperatures go up. Then I basically let the system drift and cooled it way down to about 9 or 8 degrees centigrade, and then heated it back up, and then heated it up again with the ramp. And what I'm going to show you is the actual power on this run starts somewhere in here on the time axis during the period when there's no current running. That's the next plot I'll show you. But basically, if you keep track of the inlet and outlet temperatures on the calorimeter, what you'll see is that over here, the outlet temperature is above the inlet. And that's just a characteristic signature of the calorimeters producing heat. Something is making heat during this. And with most calorimeters, you really don't believe the data until you get to a steady state situation. Then the delta T makes some sense. And it's the same thing here. But what you see is there's a very long period of time right through here where the outlet exceeds the inlet, in this case at most by 2 degrees centigrade, which is not a whole lot compared to some of the runs I've seen. But let's go back and just take a look. This particular run started off everything near room temperature. And as I heat the cell, this is using the flow calorimeter, just power it up to a set point of 60 degrees. This right in here is where the resistance of the film goes up, that I'm real convinced is an increase is due to the thermal expansion of the material. Basically, it's the thermal coefficient of resistivity. If you go and look that up in a table, it says it's about this amount. So we're looking at most here from somewhere on the order of, I guess, 27 to 29 milliohms of increase. And at this point in the run right here, what you see, there's a very small current turned on that actually starts this thing to charge. And you'll see the resistance come up and peak. And all during this time, notice the current now is coming up. This is current, I've actually listed it as what's called the inlet power, the input power. It's electrical current times the voltage across the cell that's going in. And you can see these numbers here on the order at maximum about 8 watts. And when you get the 8 watts in, you can see the temperature of the cell come on up above the calorimeter. So these yellow plots and red is the average of the two cell temperatures. On this particular run, did nothing, it made no heat, there was no evidence of any type of heat, no activity in the cell. Basically, it was very clean and clear, except when I turned the electrolysis current on. And then after cooling, real fast cooling, down to 10 degrees centigrade, then I forced it back up to room temperature and just let it sit. And it's somewhere right in here where the power takes off. Now I'll show you, I have an overlay for this thing. Let's see how the overlay works. But the power calculation, is shown in this color right here. And what's happening is right through here is the calorimeter, and normally when you're putting heat into it to keep it warm, the inlet's hotter than the outlet. And what's happening right through here is there's a switch over. There's a change between which one is hotter. And that continues on. Again, if you just look at the scale for this power, it runs essentially from right in here to 30 hours? 5 minutes, okay. So anyway, to show you this, the power level is plotted on this side, roughly about 100 watts coming out. Okay, let me show you the next run. I do have some blow-up details of those regions. I'll go ahead and jump to the next one, which is a little bit more exciting. If you take the as-deposited film, this was one where no current was turned on initially. This is the very beginning of the run, again, about a 30-hour run. And what you'll see right here, when things begin to start, this is where I poured the cell solution into an already hot beaker. The beaker was already up to near set point, poured cold solution into it, and immediately at the very top, you can see this separation between here and here. The cell temperature on the outlet, rather on the inlet, dropped. These things separated, indicating a lot of power. In fact, these temperature differences are about 14 to 15 degrees centigrade. And there's just no way to argue that was not real, even with this system with two thermocouples. So a lot of power, and again, the visual observation was an incredibly active cell, lots of carbonate being formed, and also reabsorbed somehow or redissolving back into the solution. And this thing ran and made power. In fact, you can see this window right here for a period of over 20 hours. Another key feature, once this thing started making heat, of course, the next thing was to try to add some current to it. And that's what you're seeing here, is electrical power input. And it does make a small change, and you'll see when this current was first turned on is when the palladium began charging. So the resistance went up. So, but the power actually shows up before that. In fact, I thought I'd show you the blow up. And again, if you calculate the power levels for this particular system over this whole period, they're on the order of 200 and 250 watts over that range. And again, it varies somewhat. But again, somewhat independent of the current. The current's turned off here. We see a small drop in this thing over here. I'm just letting basically the temperatures come on down and cool it. In fact, you can see that if you overlay this. What I did was force cooled it right here from 60 degrees centigrade, went ahead and let it come on down, and the power drops with that. So quite a bit of power shown on that. Let me show you just a real quick blow up here of the beginning of this run. Right in here, this is the cell temperature with no solution poured in. So it's empty. We're seeing the cell temperature come up. As soon as the cold solution was added, right in here, you start to see this separation between the inlet and outlet. And there's a little changeover, and then this large delta T that appeared. And again, this was all during no current. The current is turned on at this point, electrolysis current. So this power actually shows up before this palladium was ever charged. And of course, once we turn the current on, you see the resistance of the film going up and peak. Okay, I've probably got 1 minute left, so I'll run a little faster here. In fact, I'll save. So, thought I'd just mention this sort of a conclusion, the heat versus no heat runs. Biggest difference was the lithium carbonate formation issue. What type of formate? Is it a crystal granular form, or is it that diffusive type powdering? And then again, the cathode and resistance differences. I can show you a real quick plot of that. That was somewhat different. And this particular first run, the one that actually made the heat after electrolysis, what I want to focus on is this region right in here. Again, it's a blow up of the region where the power begins to form. And this little plot here is the actual power that shows up. Again, it's on the order of 100 watts total. But right in here, when these voltages drop, what I found that this distance, when this number right here between those two voltage levels is about plus 0.6 volts, something like that, 0.6 to 0.65 is when the power shows up. And again, somewhat surprising, but I've done many runs that didn't work, and when those voltages are outside of that window, they can either be 0 or well above a volt. I've never seen any power. Again, I don't know if that voltage is creating the power, but it seems to be like a diagnostic of some sort. It's an indicator of something. So I've sort of focused on that a little bit. And again, the run that produced heat right off the bat, just to show you its voltages. Again, this is the VCA and VRA. It's this distance right between those two. And again, it's in the 0.6 volts range. This one happened when I first put the solution in. There was about 0.6 volts between those voltage readings. So I guess just by luck, this particular run, it was ready to go. And it's sort of my indication. Well, let me conclude just briefly. You know, why no heat? Questions. Basically, I think a lot of it's related to palladium and platinum activity and the issue of foul. We have seen silicon in several of the post runs. Silicon comes obviously from the beaker that's in there. CO2 exchanges with the solution surface can be different days depending on partial pressures. Also different thermal gradients in the cell. There have been several what I call anomalous differences between the top temperature and the bottom temperature in the cell. Lithium carbonate forms, again in the heat runs, is a very fine powdery silk form, and the no heat, a coarse granular form. And then final conclusions, and I'll stop, is power levels near 200 watts sustained for at least 20 hours. In 4 different runs. We had 4 successful runs that made quite a bit of heat. The one I showed you with no charging was probably the largest heat, 200 to 300 watts for quite a long time. Unique features of this system is it's a large cell volume, 1,200 milliliters, concentrated lithium salt, and thin film palladium cathodes. At least on the surface, those are the major differences with other people that have tried this. The CO2, carbon dioxide, apparently from the air, is apparently playing a large role in catalysis in this system. There is a problem with repeatability. In fact, I've done 12 extended runs. It made no heat, gave me a lot of electrolysis issues. I was able to load the palladium, keep track of its resistance, look at voltages, but no heat signatures at all from several of those runs. And then finally, some ideas of things I'm going to try later. Basically, forcing these potentials externally with power supplies, maybe changing the water to D2O ratios, and then I think a big part, this thing I'm working on right now, is cleaning procedures for these electrodes, and then possibly CO2 partial pressure control. I think those may be something to point in the direction to get better reproducibility.
This paper is open for questions now. If the questioners need to use the microphones 1, 2, and 3 here, so if you could sort of line up over there to ask your questions, and please identify yourself when you ask. And start with microphone 1.
Douglas Morrison from Geneva. You've given 2 remarkable discoveries. One is that you can get power produced without any charging, without any electrolysis. And this is entirely different from the whole philosophy of cold fusion, which electrolysis and thing, and it's very remarkable. And the second remarkable thing is that you have said that the procedure happens very quickly. I mean, almost instantaneously you get power, there's no current. And then when you put on the current, the power rises very quickly. Now, I mean, even though 5 microns is small, this is a very, very high speed, because there's been many experiments like Mike McCoubrey and many other people who said it takes a long time to load. So, I mean, your results seem in absolute contradiction with everything that's been done for the last 9 years.
I understand your concern. In fact, there were things that surprised me as well. For example, you mentioned, well, this one, the issue of the power changing very rapidly. Of course, you got to realize this is a long 5 hours. None of this stuff, like when I turn the current on and the power actually goes up some, it takes several, certainly 30 minutes, 15 minutes before you start to see the change of that. It's not abrupt within seconds. And like the first one, when we first poured the solution in, that jumped right off to make the heat, it was probably 10 minutes or so after the solution was poured that it became obvious that this thing was actually producing the heat. In other words, it takes quite a while to develop. I understand that. I was surprised as well. I thought that electrolysis was going to be a key feature in this. That's why I set it up to run it as an electrolysis cell and to monitor that charging.
I'm David Nagel, Naval Research Laboratory. Thank you for the interesting talk. My question concerns the graph of power versus time for the first run.
Okay.
If you can find that view graph, could you explain why the power was negative early in the run, please?
Right. Yeah, that's a very, very good point. In fact, this is right here. of why the power is negative. If you take a look right through here, typically what I do is keep track, all this power indication is the flow rate times the delta T of the solution, or the delta T of the calorimeter rather. If the inlet is hotter than the outlet, that means we're putting power into the cell. And then, so that power calculation is going to be a negative number. Whereas if the outlet is hotter than the inlet, it switches. It takes typically, just to keep this cell warm, it takes several watts just to keep it at temperature. In other words, when you heat the thing up to 60 degrees C, you still have to keep power putting into it just to keep it warm. And that's where that negative number is coming from. Most of these cells that I've run is typically about 80 watts or so is what's required. Say if I want to keep this at 60 degrees centigrade, it takes typically 60 watts. And what you're going to see, obviously, when you start cooling the system real fast, then you're taking heat out of these cells. And that shows up as a positive power spike in these plots. In fact, right here is one. This was during the cooling, where you see that power going positive. That's artificial. All I did was cool the cell. When I cooled the cell down from 60 degrees to 10 degrees centigrade, I took heat out of the cell. So therefore, the power signature goes up just because the temperature is reversed on the inlet and outlet. That's a very good question. It's quite confusing. Did I answer it pretty well, or?
Heinrich Horan from University of New South Wales in Sydney. Following the question of Dr. Morrison, where you have no electrical current, you have an energy production. And if you divide the energy per atom of palladium, how many electron volts will you get out? So energy production per atom. Did you get electron volts or 10, 100 electron volts per atom?
I'm not clear to understand the question. You're talking about the power out,
Yeah.
how much? Or
How much energy do you produce per palladium atom
okay.
during this 20 hours non-electrolytic current
Mhm.
production?
In other words, you're comparing how much power I put into the system to the power that came out.
No, per atom.
Integrate the power and count. What I've done, in fact, it's related to one of my choices to find out where this power could have come from. For example, lithium carbonate is an exothermic formation. If you form that, you can look up its heat of formation.
Sorry, I was only asking about the number of the
Yeah, I don't know the number right off the top of my head, but I do know I've calculated the total energy that was produced during this run and compare that to the total energy that could have been produced by the lithium carbonate formation. And it turns out that if you took all the lithium in this solution and all the lithium converted to carbonate, it would account for this energy. It would. If all the lithium in my solution, all of it came out, it would just about account for this power, or this energy, total energy. However, the solutions after the run and before run have been analyzed using atomic absorption spectroscopy. The amount of lithium dropped about 5% from the original. It was when I started the run till afterwards, we had about a 5% change in the lithium concentration. That was exactly what I was looking for, that there's got to be a chemical explanation, and certainly that lithium carbonate being very exothermic is a possibility.
Gene Mallove, Cohesion Technology and Infinite Energy. Similar question. Calculated, obviously, we've got about 14.5 megajoules of energy release. And if you know approximately the number of moles of palladium, or if someone else knows, we know how
The
many.
moles of palladium,
Yes.
I have a rough idea, it's on the order of 3 milligrams. And of course, you could back that out into a mole thing, but if you go through just the density times the area and the thickness, it's about a few milligrams. It's not much palladium. It's a very small amount. In fact, that's what makes me think this is some type of surface-activated catalysis. And again, I'm not a theorist on a lot of chemistry. The catalysis in chemistry is quite complex. I've done quite a bit of reading, don't understand a lot of it, but apparently I'm in league with quite a few people.
But you're quite clear that only 5% of the lithium
That was double
combined.
checked and rechecked. That's exactly right. No more than 5% came out of the solution. But see, it's related. Remember I told you about the idea that this lithium carbonate is forming and appears to be being reabsorbed somehow. I think that's a key feature, because many runs I've done, I've actually taken solutions and run them with just electrolysis, those that produce no heat, and formed a lot of carbonate and took out 90% of the lithium. Took it over to the chem lab, they analyzed it, only 10% of the lithium was left. Those produce no heat. But for some reason, and I think this may be a key factor, is that carbonate that's forming is being redissolved. And again, you talk with at least the chemists I've talked with, they say the lithium carbonate does not dissolve in this solution. When it forms, it sinks to the bottom and sits there. In the runs that produce no heat, that's exactly what it did. It sinks like a rock and just forms. But for some reason, we got this dissolving.
C'erano sono stati laboratori. So I have three questions. First one, you told you have like a square wave power supply on and off, but the period of your on power, off power. The second question, you have voltage controlled or current controlled power supply. And the third question, when you have open cell, you have some light water coming inside. How you can control the amount of light water coming in your solution?
How do I control the amount of light water coming in?
Yes, because
Okay.
heavy water absorbs.
Right, and that's a good point. In fact, this solution starts off with D2O and lithium hydroxide monohydrate that has water in it. In fact, if you just calculate the H2O with the 2.5 mole, you get about a 5% mole fraction of water. The reason I didn't let that concern me too much is you're going to get water vapor in the air anyway if you have an open cell. That's going to be a train. So that's your...
No, I think there are two kinds of problems. The first one, okay, you add some light water because leaking is okay, but over time there is the water coming from environment to your cell.
Right.
So did you check the amount of light water coming from?
No, I don't have the diagnostics for that.
Okay.
But good question.
Second, you have, which one is your period of on-off? You give power for 1 minute, 1 second, 1 hour?
Oh, good question. Yeah. What I run is a 30-second total cycle time. And
Yeah,
basically,
yeah.
the current's on for 18 seconds and then 12 seconds off. And that comes out to about a 60% duty cycle. But the idea was sort of to mimic DC, was the idea. I'm not trying to get into changing the current that much. But the main reason I have to turn the current off is so I can read the voltage, read the resistance of the film. The way the electronics works out, you can't read that resistance while you're running the current. Does
We
that
only have about 5 more minutes or
But 18 seconds to 12 seconds is that cycle.
Voltage or current control of the power supply?
I have current, constant current.
Constant
Running constant current all the time.
Scott Chubb, Naval Research Laboratory.
Mm-hmm.
I was curious, did you really vary the H2O, or is that something you're going to do?
Did I bury it?
Vary it.
Actually, I haven't done that yet. Those are some ideas for future work.
Well,
But I have a feeling it may be related. And what I've done, for example, some runs with lithium hydroxide anhydrous versus the lithium hydroxide monohydrate. I've done those two, where you can control the initial amount of water that you put in there. And I have seen voltage differences with those.
Yeah.
I have not yet to get a run, though, with the anhydrous form.
That's an interesting point, because there is evidence that you can get helium-3, and when you have mixtures. Arata in particular had D2O and
I can tell you some interesting things. I did.
IOH.
Yeah, just a week ago, I added some regular water to this solution that did not produce any heat. And I saw this in some abstracts last night, this issue of what happens when you do that. If you take a look, what I'm plotting right here is essentially the cell. The black one is the bottom cell temperature, and the white plot is the cell temperature at the top. Now, this was a system that basically made no heat. I heated it up, just let it cool back down, heated it up again. There's no thermal power coming out of the system. And up until this point right here, there was no current running through it. But notice, once you get going, before the current is turned on, what happened with this particular, this was a small beaker, a little 250 milliliter, and it was evaporating at the top. So I just went ahead and put some distilled water, deionized water, cold room temperature. And what I expected to happen with these temperatures is that when I added that water, I expected the temperature to drop at the top. I also expected the temperature at the bottom to drop, and it didn't. The bottom cell temperature actually went up, and this one came down and continued to go down. The next step, you see this change right here, I stirred the solution with a stirring stick, just manually stirred it very vigorously, and you see these temperatures start to approach each other. And as soon as after the stirring was done, the temperature separated again, related somehow to this water amount. This was regular H2O added to the solution.
Well, it sounds like an interesting thing to monitor.
It is. That's why I thought it's an idea to pursue.
Hi, Larry Forsley, GWK. Did you monitor the pH throughout the experiment?
I attempted to. The pH it starts off when you mix the stuff up initially at room temperature, you do 20 degrees centigrade, it's about 12.5. What you find, of course, is the pH is temperature sensitive. I have temperature compensation. So I have several ones where I've recorded that. But what I found is that typically this pH meter stuck in this very high, highly basic solution tends to become sensitized to this, particularly at 60 degrees centigrade. It begins to evaporate quite a bit. So what I've resorted to recently is just sampling the pH occasionally. But I'm real baffled. Many times the pH is below 11 at 60 degrees, and sometimes it's 10.5. And I've even taken that at 60 degrees, added more hydroxide to it, and it does not go up.
So there's something buffering your solution. There's something buffering your solution in there.
That's what I'm thinking.
And then you've got all the CO2 going, which is driving it acidic.
The CO2, I guess, would be acidic when it comes in.
Last question.
Yeah, Huggins University, Kiel, Germany. I want to make a comment with regard to the first comments from our friend Douglas Morrison, who said that this is remarkably different from the total literature in this field. One of the reasons is that you see the excess heat or generation of thermal power with no electrolysis. That indeed is, so far as I can tell, new for palladium, but this has been reported by the group of Gintelli in Siena, Italy, in the case of nickel, under quite different elevated temperature conditions. So it may well be that electrolysis is not a key issue. Something else is happening which causes these effects, and the electrolysis may or may not be necessary.
I think I agree. My comment with that question is that maybe electrolysis is needed in some cases, that you need to load part of the bulk to get the right surface properties. And other samples, the surface properties are there without loading. In other words, there may be cases where you have to run current to just get it to take off. But I agree. It looks to me, again, not an expert on much of the theory, but my feeling is that it is some type of near surface solution effect, some type of interface catalysis.
Very good. Thank you.
Thank you, George.
Our next speaker, Dr. Masui, is from the New Energy and Industrial Technology Development Organization, Japan, and he is talking about excess heat measurements and winter detection measurements, experiments in the NHE program.
Good morning, ladies and gentlemen. My name is Matsui, Kazakh Matsui of the Institute of Applied Energy. I'm here to report the summary of the results of our project. I mean, we call it New Hydrogen Energy Project. It was Japanese national project since 1993. I'm speaking on behalf of the project. I'm going to touch the subjects relating to heat and nuclear both. And the other subjects, very interesting, I think, material, will be covered by Dr. Asami on Wednesday. Well, then those are the people who, the authors of this today's my presentation. Well, let me touch briefly our project. I suppose that most of you are familiar with our project. I mean, since I told you that November 1993 is 5 years ago. Our project for 4 years, I mean, originally designed for 4 years. We have extended 1 year, then total, the time length is 4 years and 4 months. We spent almost, very closely, $20 million equivalent for this time, for this national project. And then another, maybe something like $6 million equivalent for the support to the universities. This money mostly spent for the upgrading the apparatus, facilities of the universities from Hokkaido to down to Kyushu to support our basic knowledge about this field of study. First of all, I will speak about the excess heat, I mean the heat stuff. In spite of the very interesting or encouraging presentation by Dr. Crane, I'm afraid to say that my one is a little bit, is not encouraging. Well, but because our study was kind of first of all, we started to try to prove the reproducibility of the experiment from prior art. And those are the lists which we have tested in our laboratory, namely 6 types of the cells. One, the famous one, Professor Fleischmann and Professor Pons types of the cells. There are 2 kinds of them. It's open cell. It's, you are very familiar with that. And secondly, we call it fuel cell type cell. It's developed by Dr. Kunimatsu in Japan. It's closed system. And then third, Dr. Makubri and his colleagues developed a mass flow parametric system. Fourth is Dr. Jerami's very innovative electric cell. And fifth and sixth, that's our own flow parametric system. Those systems, very fine, nothing wrong. I mean, hardware, software, very fine. I mean, if there is excess heat or something like that, more than 1 to 5% of input power, we're sure we can get it. I mean, the software, hardware, very fine, everything. But after the efforts to increase the deuterium loading to the palladium and devise electricity conditions, the second cell is what we call it IJ cells. IJ stands for in Japan, gave us the similar results of excess heat claimed by the researchers. That's what we have reported at ICCF-7. Okay. But the others, no, including our system, didn't give us any obvious excess heat. I mean, obvious excess heat means this should be consistent because of most of the tests for average 1 month, some of them 2 months, something like that. we want to have the consistent series of the data. We do not like to look at only one day, 1 hour, 2 hours data. No, we wanted to have a consistent data set. In that sense, the only second one, but not all of them, but gave us the heat. The reason why we did have the long series of the consistent heat, because our primary objective is to develop the device, utilize this kind of the energy for further practical use. That's the reason why. And also to find out the mechanism of the anomalous reaction and so forth. It needs some consistency. Then we did have a detection of excess heat with this system, but we couldn't get the excess heat with the other system. Then we thought, what's going on there? Then this is the one of the way which we try to find out what's going on there. This is the original ideal cell. Well, the basic philosophy idea is to transfer that ideal cell to the flow calorimetry system as it is. This is not the flow calorimetry system. This is to measure the temperature of the electrolyte or a flow, preparing the calibration curve, and then estimating the excess heat. Then here, transferring this ideal cell to our flow calorimetry system, we can analyze the phenomena in both ways. One is using that calibration curve. Secondly, with the calorimetric system. This is an example of what we have found out. It might be a little bit hard to recognize, but this black one, this is the excess heat determined by the flow calorimetric system. Well, there are some fluctuation based on the flow rate change, but it's nothing. But please look at this light blue lines. This is the excess heat estimated by the calibration curve. It means estimated by the temperatures of electrolyte and electrode. Well, there is some, of course, quite a big deviation. And at that time, we had a hypothesis. One is something wrong with the FCS, flow calorimetry system, or something wrong with the ID system or calculation system. Then we took the series of the experiments to find out the cause, or which is the correct answer. The final, our present conclusion is FCS is correct, but no, this is false. There are some other data which I can show you, but maybe this is the typical experiments. This is the that I just saw in the FCS with the dummy heater. And of course, electricity is going on. Here, this series of the test, only with the dummy heater. Input like 1 watt and 2 watt. Both systems, FCS and cathode temperature, both detect the dummy heater input. Very fine. But FCS, because the cooling tube is outside the cell, therefore sensitivity is not so good. Therefore, the black one follows the light blue one. Light blue one is the temperature, measuring the temperature of the electrolyte, therefore it's quicker, of course. It's very reasonable, I think. And then here, we put the electrolysis power. Then, therefore, the calibration type of the measurement, estimation of excess heat have given us excess heat, but pro calorimetric system no. And we put some dummy heat on this electricity power. Here we increased the electricity current, then the temperature of cathode and electrolyte have risen, but no net heat output. Then, well, there are other some the things which I should mention, but because of the time limitation, and then maybe this afternoon you can see the poster of our presentation. I hope you can look at it a little bit more detail. Then this is the result, the reason why we did conclude the heat which we have observed through ICCF was false. There are a lot of other informations which we have obtained through the series of our heat experiments. By the way, the total number of our electricity cell experiments sums up about 500. 500 is not so easy. 500 with these 6 electricity cells for 4 years. If the one experiment stands for 1 month, 30 days multiplied by 500, 15,000 days of electricity cells without the preparation. Here, the conclusion of our excess heat measurement. No apparent excess heat measurement observed over instrumentation limits. Of course, there might be some. But therefore, the secondary, we may say that we failed to verify the existence of excess heat or which level was expected at the beginning of the project. Which we thought we might be able to develop the practical use of that heat. Then, right now we say that it is very hard at present time to utilize the new hydrogen energy for practical purposes with the present science and technology industry. But of course, we are not to deny the possible existence of solid-state nuclear reactions or the other things, and it's possible trace amount of the heat. However, the phenomenon is still within the scope of fundamental research which diamond mine may contain. Thank you. This is, sorry, I'd like to teach at 5 minutes more. And then if I hope to have 10 minutes more, but okay, I rush the second topics about the nuclear stuff. Well, the conclusion of our nuclear stuff detection experiments, the first one, for this field, we did have a very intensive series of experiments too. But our experiences here, again, most of them were negative. But I don't get into the detail. There might be some debates or discussions regarding to this, our conclusions, present conclusions. Like perhaps Dr. Iwamura may have something to say about this, but I think Dr. Iwamura has a chance to speak, then I will let him speak. And then secondly, our project is kind of international collaborative work, and then we had researchers from abroad. Then this series of experiments is done by the Dr. Andrei Lipson of the Russian Academy of Science. I suppose that you may hear from him the detail of his experiment, but I rush the several things which seems very interesting. I mean, this was done through the collaboration with the other universities of Japan, like Hokkaido and Tohoku. I mean, Hokkaido is maybe, I think, Dr. Mizuno's experiments. I mean, Dr. Mizuno and his colleagues, and then Tohoku, Kasagi, Professor Kasagi, and Professor Takahashi of Osaka. Then those are all the measurement says maybe some. This is just one of the example which was done, I think, at the Hokkaido University. And this is the detection of neutron. There might be some symptom of the existence of the neutron from his sample. I mean, heterostructure, his sample, like palladium film. One side palladium oxide, the other side gold. Then there are some other very interesting results with his sample. And then perhaps tomorrow, I suppose that Professor Kasagi will show up here. And then I think he can explain to you the importance of the result. This is his famous the experiments. It's a bombardment by the deuteron. And then he's observing the anomalous enhancement of the reaction. I suppose there might be some more debates about his experiment, of course. But if it's true, I think this might give us a very important suggestions in future. I don't go into the detail, but I'd like to tell you again that I suppose that Professor Kasagi will show up maybe tomorrow and speak about it. But this is done the collaborative work with the Dr. Lipson and the Professor Kasagi. The others, well, this one is a little bit, we are a little bit hesitate to show you. This is the heading 4. We detected the heading 4, but this series of that test was originally intended to try to find out the heading 4 from the palladium samples, which with the excess heat, because we didn't have any electrode which gave us excess heat. Then, okay, but anyway, we will test this the whole apparatus for the heading 4. Then we picked up the 4 samples. and two of them are the wire, famous Japanese type of the equipment. One of those two wires gave us a helpful. Well, this is helpful. We are pretty sure, but we were a little bit reluctant that this helpful from the electrode, the wire, that's only the accountable explanation, but still, because this is the only one detection, therefore we are pretty much hesitate to speak out. But those people forced me to speak about it. But anyway, let me conclude. What is the conclusion? I mean, those are for the nuclear stuff. We did have the faint, some the detection or measurement. Then we say, the further follow-up works maybe was by some other researchers, by some other means and something like that. But from the standpoint of our project, I have to say this way. Although there are not any clear and strong evidence of anomalous reactions in our laboratory to justify the continuation of the so-called new hydrogen energy development project in Japan. But there seems to be some symptoms or some experiments for new area of the research, including the nuclear physics and others, of course. But we like to add, we should be very careful. Rigorous and careful experiments are the least requirements, of course, like all of you know, agrees. Thank you very much.
We're running short of time. We have time for 2 or 3 very quick questions, please.
So I have a quick question. Could you put that curve up, please, of your flow calorimetry versus the control? When you first put on the electrolysis current, the flow calorimeter shows its output going down. Could you explain that, please?
You mean this one?
No. The one that showed, yes. Why, when you put on the electrolysis current, does the flow calorimeter show a decrease going down?
It's easy. Because the way to evaluate excess heat, the balance, okay? Output energy divided by input, okay? When you turn on the current, it says, okay, the power there, but the temperatures coming later, therefore very low minus.
Mike Mealich, Naval Postgraduate School. In your very last slide, you suggest careful and rigorous experiments in nuclear phenomena associated with this series of studies that you're talking about. Do any such experiments continue in Japan at this time? Do you have intention of continuing such studies?
Well, for the national project, like so-called NHE project, we don't expect to continue. But we are now applying for the new, a little bit more fundamental research type of the research study for funds from the government. But this is again the international collaborative works. That's for ourselves. And then the other activities in Japan, well, of course, with the British people and the other universities, activities still going on.
Mike 3.
Stephen Rushwitz, a graduate student from Manitoba, Canada. Just a quick question on the cathode. This is very loud. On the cathode structure, were they thin wires or were there large areas? Like the last presenter had a 7.5 centimeter squared area, and I'm wondering if different.
I must say I preferred Fred's introduction music to the music that they gave for me. Necessarily. How's that? And that the development of this field has been fraught with what I've always called an apparent irreproducibility, and the fact that we cannot reproduce our experiments one to the next, as was characterized by the first two lectures this morning, is to me the principal problem which strangles the development of the field. What I thought I'd do today is describe just how bad this irreproducibility is, explain that there are materials issues associated with that irreproducibility, and suggest perhaps some pathways that we might break out of this hammerlock. You remember the initial current density, we don't know which. Current density obviously would affect, thank you. Current density obviously would affect the loading. The current might affect the deuteron flux in and out of the surface, some photon generations, something we don't know yet what. In addition, you need to hold this system for some extended period of time, although if you have a 5 micron film, apparently that time isn't very long. Given that we achieve these conditions, we hope that we will achieve an anomalous state, perhaps what Ed Storms describes as a nuclear active state. We get some evidence of excess heat and possibly evidence of a nuclear process. What I'm going to describe is a series of experiments designed to really institute the conditions that we think we need. High deuterium to palladium loadings, as measured by the resistance ratio, at high currents for long times. What I've done is scanned through the data that we've accumulated over the 8 or 9 years that we've been working in this field, and selected 26 nominally identical current ramps, increasing current, measuring the resistance ratio. I'm sorry I didn't bring this slide. I presented it probably at every ICCF conference, so you should have memorized it. But we measure the resistance ratio of the resistance in the presence of deuterium to the resistance of the cathode before any deuterium or hydrogen has entered into the lattice. And the axis 0 to 1 D to PD ratio. The curve goes up through a maximum at approximately 1.96 resistance ratio at a loading of about 0.74. And the high loading condition is really this right-hand branch. What I want to do in all cases, what we're striving to do, is to get the resistance ratio as low as possible on the right-hand side of this resistance maximum, and as high a current as possible to give us the best opportunity to observe anomalous excess heat. Now, having said that, I've selected 26 identical experiments, one hydrogen experiment, the rest of them deuterium experiments. The result is seemingly incomprehensible. The 26 experiments yield 26 unique and entirely different results, despite the fact that we've taken extreme precautions to maintain the electrolyte and the electrode and electrode surface condition the same in all experiments. The current ramps are at the same rate. In this curve that I'm about to show you, the points that are solid are those for which we observed excess power at more than a 3 sigma confidence level. All other open points, no believable excess power was observed. Okay, this actually is a catalogue of failure, if you like. Well, the first interpretation of this slide is that the SRI group is incompetent. We've done the same experiment 26 times. We've obtained these 26 wonderful results, all of them different. If you notice, they all start at a current density of 33 milliamps per square centimeter, increasing current density in this direction. What we're trying to do is drive the resistance down while we drive the current up. As you can see, in general, we do it, but the trajectories chosen by the cathodes in all of these experiments are remarkably disparate. In fact, depressingly disparate. There is a trend of a sort that the excess power tends to be observed at high current densities and towards low resistance ratio, as I suggested, but any sense of a mathematical predictive quantification of this effect, you certainly can't discover it by looking at those data. Why not? Well, we're measuring resistance ratio. The resistance ratio is affected by things other than the absorption of deuterium into the palladium lattice. Electrodeposition and absorption of light elements, boron, beryllium, carbon, all affect the resistance. The absorption of protons, which happen to be in the electrolyte, changes the resistance ratio without changing the D to PD ratio necessarily. Sort of hydrogen process, mechanical changes introduced into the electrode by the cold work associated with the absorption of deuterium into the palladium lattice. Electrode gross dimensional changes, which Ed Storms pointed out, the tendency towards a sphere, cathodes becoming more spherical in shape as they are exercised and cycled, and cracking. In an attempt to avoid all of the variables which affect the resistance, other than the one that I'm interested in, I've attempted a new normalization of the data. I've simply taken the resistance ratio as measured, divided by the resistance ratio of the electrode under some standard condition, and I've arbitrarily selected as a standard condition 33 milliamps per square centimeter. So what I'm saying is that the electrode has achieved its equilibrium state of loading at 33 milliamps per square centimeter. I chose that to be on the right-hand side of the resistance maximum, so that all changes, all reductions that we observe in the resistance ratio can then be ascribed to the uptake of deuterium, and deuterium alone, because the effects that I'm talking about here have either all occurred or do not occur on the time scale of the current ramps. I don't have time to explain this in detail, but what I'm seeking is a variable which responds only to the uptake of the deuterium. If I renormalize the same 26 data sets as I showed you before, according to this method, it certainly looks a little bit better, but you'll notice that I've cheated twice. First is the normalization requires all data to go through this point. And it's a logarithmic plot, which always makes things look better. When you take this into account, you might say, well, this hasn't helped, but in fact it has helped. I submit that the data which are presented on this slide fall into one of 3 different distinct categories of results. Data can be grouped with surprising precision into 3 discrete modes of response. Mode A, approximately linear decrease in resistance with logarithmic increase in current density, an equation which covers these data here. I won't go into the details. Mode B initially follows the linear reduction in resistance with logarithmic increase in current density, but then it's followed by a rapid increase in resistance. The cathode attempts to load, and then for reasons which I want to discuss a little bit further, suddenly gives up. It can't get any more loaded. The resistance ratio can't decrease below a certain value. The cathode precipitously deloads. The third mode is a shallow decrease and increase in resistance. This is a cathode that really doesn't have any capacity to load, probably because the interface is in some way damaged electrochemically, or the electrolyte conditions are simply not conducive to good loading. I can show you the breakout of data into those three groups. The important thing, this is the linear, log linear decrease. I've drawn some dotted lines to guide your eyes, but you can see the thick green line is in fact a light water, a proton result. So this behavior doesn't care whether it's a proton or a deuteron that you're loading into the lattice. The log linear decrease seems to be well obeyed, and you'll find that the experiments which have yielded excess heat tend to fall on this mode A curve. This decrease is very, very significant. It corresponds to extraordinary degrees of loading. Some of these loadings are 0.97 D to PD, for example. This is a mode A behavior, and I submit this is the behavior we want, we desire, we seek to achieve, so that we can examine the anomalous phenomenon that we've gathered here to discuss. Mode B behavior it really starts out the same. Follows this, these are the same hatched lines that I had on the last curve. If it comes down, everything is doing very, very well. Cathode is loading well, and at some point it says, whoops, and they deload, precipitously deload, and never reload again. So there is a mechanism which, once you've embarked upon the trajectory that you desire to follow, a precipitous failure, an abrupt failure occurs which prevents the cathode from loading any further, and worse, it causes a rapid deloading towards the equilibrium loading condition. Mode C is similar in general shape to mode B, but it's a much shallower response. This is really a cathode which, all of these are cathodes which didn't really load very much, and at high current densities deloaded just a little bit. I submit that these experiments are simply experiments where we have failed to manage the electrochemical conditions with sufficient skill to obtain a cathode that was capable of being loaded electrochemically to any degree. So this is bad electrochemistry. What's wrong with the other two? In particular, why does mode B occur when we're seeking to achieve loading according to the mode A trajectory? What I've done here is plotted the equilibrium pressure as observed by Baranowski needed to obtain the resistance ratio that would correspond to this axis. So here we have 101 megapascals corresponding to reduced resistance ratio of 0.99. As you notice, the pressure is increasing. 441 megapascals, for people not familiar with it, is 4,410 atmospheres of deuterium pressure. These are very extreme pressures. What it looks like in mode B, if we follow the trajectory, this is a representation of all of the data in mode B behavior, but it's surprisingly consistent. Somewhere between 300 and 500 megapascals, it looks like the electrode simply fails. I submit that the failure is mechanical. There are voids inside the palladium, which when loaded to these pressures, simply yield, and this is a number close to the yield strength of palladium. We don't actually know what the yield strength of PDD 0.9 is. This is a number not unreasonable for the yield strength of palladium. So I'm submitting that the mode A behavior fails mechanically. Both mode A and mode B, we have obtained the correct electrochemical conditions, that the mechanical character of the palladium is insufficient, just too weak to tolerate the high loadings that we need to obtain the resistance ratios that we're looking for and the chemical potential of deuterium in the lattice that we're seeking. Yeah, in fact, how much time do we have?
We have about 8 minutes.
Be the shortest lecture of my life. We have some independent evidence that I think it's very recently obtained, in fact, that this mechanical disruption does in fact occur and does prevent us obtaining high loadings. What we're doing is working along the lines that have been suggested to us by Arata, Professor Arata and Dr. Zhang, of a double structured cathode. That is a palladium cathode in our normal mode, 4 millimeters outside dimension drilled out, with a 2 millimeter hole packed with palladium black and then welded closed. So we're trying to make a pressurized void space inside the palladium cathode, a very small version of the Arata-Zhang experiment. This is the first experiment we ran in this mode. We're actually measuring the resistance ratio twice. One in the space that's hollowed out, the double structured region, one in a length of solid palladium adjoining the hollowed out region. The discrepancy between the two is not important, and the two clearly load. There's some difference in the dynamics of loading between the hollowed out section and the solid section. But what happens is resistance ratio increases, desirable, as current ramp increases. This is good. Resistance ratio comes down on the right-hand side of the resistance maximum as we desire. And at some point, the cathode simply failed. At this point, at a resistance ratio of about 1.8, the cathode ruptured. The gas that was pressurized inside the Arata-Zhang double-structured void was released, and the experiment was really dead at that point, although we continued with it for some considerable period of time. We were doing calorimetry. This will also be the smallest excess power result that ever shown. All we observed from that cathode was, this is plus or minus 20 millivolts we're talking about. This excess heat here is simply the heat of absorption of deuterium into palladium. This is entirely chemical energy. There was no excess heat associated with this experiment at all. Everything we saw was chemical, like 13 kilojoules per mole. So although we obtained quite a high pressure inside the Arata-Zhang cathode, we did so for only a very fleeting moment, and there was no obvious excess heat associated with that. But the failure, which occurred at a resistance ratio of 1.8, corresponds to a pressure of about 400 megapascals inside the cathode. The cathode failed because it was doomed to fail, because we achieved a pressure inside the hollow structured cathode sufficient to rupture the cathode wall. I don't know how well this will show up. Not especially well, actually. That was probably better. These were made electronically, which isn't my choice, just as I left. But basically, this is the cathode. It's something like 5 centimeters long, 4 millimeters in diameter. And although you can't see it at all, this is the rupture. I mean, the cathode distended, blistered, and voided at this point, not associated with the weld at all. It's beyond the weld, although it might be in the heat-affected zone. We simply obtained a pressure inside this cathode which was too great. Cathode yielded at a pressure somewhere between 3,000 and 4,000 atmospheres of D2. I have some conclusions. So, what have we learned? I think a great deal has been resolved regarding the electrochemical conditions which affect deuterium electroabsorption, the loading of deuterium into palladium. But there seems to be a materials-related variability in deuterium loading, which varies from cathode to cathode, which introduces a huge degree of irreproducibility into our experiments. I submit, although I haven't proved, that this variability is entirely mechanically associated. It has to do with the yield strength of palladium in its impure and defective state, and in the presence of deuterium and the cold work introduced by putting deuterium into the cathode. We have characterized two extreme modes of behavior, the log linear reduction and resistance, which sometimes yields extraordinary values of loading, extraordinary values of chemical potential, and mostly, but not always, anomalous excess heat. I'm claiming that the reason for premature failure of my mode B response is mechanical disruption. I showed you the Erasmus experiment. There may be ways to help this. The group at Aeneas, Garamuzzi, Vittorio Violanti, and so forth, have described a procedure in which you allow the cathode to relax. You pulse it on and allow the mechanical strains to be relieved at a lower current density. We've tried this means of cycling, and it appears indeed to help solve this mechanical problem. Small particles are suggested. When I presented this conclusion at a workshop in ASTI at the end of last year, Bob Huggins pointed out that small particles are not subject to this lattice disruption failure. Also, gas loading is good. Rather than electrochemical, if we externally pressurize, the stresses are applied from the outside rather than the inside, so we're less likely to cause lattice disruption. Suggests the experiments of Arata. Talbot Chubb is attempting to do a gas pressure equivalent of the Arata experiment, which might very well be in the right direction. I also direct you to the presentations and thoughts of Enrico and Joe Weissman and Dick Summerall. The last one, electromigration, may be a way of achieving high activities without obtaining these mechanical disruption effects. Thank you.
We have time for only one or two questions. Please come to the microphone.
Can you hear? Yes, it is working. Huggins, Kiel in Germany. If a problem is the cracking during operation or during loading, I just call your attention to a scheme that's used by at least one of the Japanese companies in the battery business. You can reduce this problem, the nucleation of cracks, by increasing the yield strength of the metal. And I'm sure you remember the experiments that were done some years ago with extremely high purity palladium, which formed cracks almost by looking at them. So I just suggest as people look to the future and think of alternative materials, that you think of solid solution hardening, which does indeed prevent formation of cracks in some alloys.
I think it's a very wise point, and what Bob is suggesting is that high purity may not be the answer. And for cleanliness and ease of defining the conditions of your experiment, you obviously seek the most pure materials that you can work with, but it's very likely that if my conjecture is correct, high purity materials are doomed to failure. And something I didn't point out is that most of the data sets which took what I described as the mode A trajectories, most of the cathodes, 90% of the cathodes that fell into that set were the least pure palladium that we have ever had in our hands. Impurity clearly is desirable. That actually is a stupid statement. Some degree of controlled dosing is clearly desirable in order to prevent this cracking phenomenon. But that's a huge matrix of experiments. We simply don't have the metallurgical resource to pursue that pathway.
Dennis Cravens from CETI. On your three different types of trajectories, do you see any difference in the volume expansion? Thinking about Ed Storm's volume thing, are the B and C, do they expand more, or did you make that measurement? And then the second thing on the impurities, have you checked the calcium? You want to pin the plane so they don't slip while it's happening. Calcium in particular. Do you know those numbers?
Yeah, and the most significant impurity in this Engelhardt Lot 1 material that was so successful for us, the most significant impurity was calcium. I know the numbers. I haven't thought to compare them data set by data set, but I could.
What about the volume expansion?
We haven't done that in any systematic way.
My guess is your A types will not swell as much.
Yeah, this is along the lines of what Ed has been talking about. Maybe. I think if you've got any void space in there at all, then mechanical disruption is essentially inevitable. So excess free volume is clearly bad.
Mike, thank you.
We now welcome Professor Takahashi, who I dare say is going to talk to us about the production of energetic tritons and alpha particles, a subject which I think Professor Takahashi will arouse as much controversy as any of the topics which have been raised so far.
Excuse me. Thank you, Professor Fleischmann, for a nice introduction. We have done pioneer studies under the so-called New Hydrogen Energy Project for basic research of the Japanese Ministry of International Trade and Industry. And today, I want to make a summary presentation about our results for three types of experiments. Yeah, one is the open cell experiment. The second one is the closed cell experiment. Third one is the neutron beam implantation experiment, with which we have got some interesting results. And also, finally, we will make some conclusion together with some modeling of some anomalous nuclear phenomena. And this time, I came here with three of my students, and each of students will present in poster session with each topic, so you can see detail. This afternoon and tomorrow, we have three posters, and also I have one summary presentation here and poster this afternoon. And okay. Already in the past ICCF conference, I have already shown the results of open cell electrolysis using this kind of sort of twin type system using two identical electrolysis systems, one for foreground experiment, one for background, running simultaneously and measuring nuclear radiation possibly coming from cell for X-ray using cadmium telluride detectors and for neutrons to Ne213 detectors using a somewhat sophisticated system for spectrometry, mostly two-dimensional analysis we are doing. And watching the correlation between calorimetry, excess heat, and the nuclear radiation for either foreground and background cell. This time I only show the typical results because we have not gotten very exciting results after the Hokkaido conference. This is a typical result I have shown in the Monte Carlo conference for the typical excess heat we observed with open cell. This is a background one. So with only a positive excess heat in the foreground one. However, we did not see any correlation with radiation with this excess heat phenomenon. Here, this is X-ray for the characteristic X-ray from radium. If we have a high-energy particle in radium, we should have about 22 keV X-ray. But this is just a background area, so we don't see any X-ray. We don't have either neutron increase, we have no neutron increase. So we have no correlation between excess heat phenomenon we observed and nuclear radiation in this case. So I'm hurrying up to go to the closed cell experiment. For this we have also a poster presentation this time. So this is a closed cell. And we are doing flow calorimetry to detect the excess heat coming out from the cell. And also measuring in situ the D/PD ratio from the pressure change of this upper cell of the cell. And also monitoring the neutron by helium-3 counter outside. And also we are making analysis for the gas in this upper room of the cell before and after the electrolysis run by using a quadrupole mass spectrometer. And also we are also making a tritium activity analysis based on the liquid scintillation counting technique. Here again I only show some typical example of excess heat coming out by flow calorimetry. In this case, this is a D/PD ratio as a function of time. This is the input and output. This is the excess heat coming out. And in some time period, we saw the excess heat somewhat meaningful over plus 3 sigma confidence level of error bar. So we are somewhat confident of the excess heat coming out. But, okay. And to see the correlation with nuclear product, we are especially interested in this case to observe the helium-4 coming out from the gas in the upper room of the electrolysis cell. And we have improved the quadrupole mass spectrometer after the Hokkaido conference to higher sensitivity of helium detection, and now we can observe this kind of spectrum for helium-4 compared with the molecular criteria around here. Using this system, this time we have some, I think, significant results, however, only in few cases. So let me summarize the result of electrolysis experiment, open cell experiment. This is the statistics of positive results we have obtained out out of 20 experiments, we observed only 3 positive excess heat and 1 neutron, somewhat meaningful, and 5 X-ray signal, but without any correlation between these events. So we don't see any correlation between measured excess heat and nuclear radiation, in this case, of open cell. And in the case of closed cell experiments, we have done about 11 experiments on this table, and we saw 4 excess heat coming out. And we saw only in one case some meaningful level of neutron increase and no tritium increase. And for helium, we have seen in 6 cases somewhat meaningful increase. Let me show the example for helium for analysis for the latest 4 experiments after we improved the product for mass spectrometer. And we are comparing here the helium for atomic number before and after electrolysis. And before electrolysis, we have about 10 to the 15th atom in the upper room of cell. And after the experiment, in this case, it increased 15 times or so. It's a net increase. And in this case, we don't see very clear excess heat. However, it took a very long run, about 720 hours. So we might have very slight excess heat accumulated for a very long time. We are not very sure about this. And in the second one, we saw also some increase of helium-4. In this case, we saw some neutron coming out, but no heat. In this case, almost background and so on. So some cases we have got positive data for helium-4 production. Now, coming to the deuteron ion beam implantation type experiment to see the possible underlying nuclear physics process in so-called cold fusion experiment. This must be some kind of non-DD type fusion, because by using a known D plus D fusion, we can't explain the results. So I'll be assuming, for example, this kind of so-called multi-body fusion. This is a case of 3-body fusion for outgoing branches, going to the lithium-6 ground state via electromagnetic transition, and other 3 are for emitting high-energy charge particles. In this case, with our latest experiment,